Welcome everyone. I am Rati Ludhani, pursuing PhD from IIT Bombay, Department of Mathematics. So today we will discuss some sample questions related to week 2. So I hope you all have gone through the lecture 3 and 4. Is it?
Yes, ma'am.
Yeah, great. Okay, so let's start the lecture, tutorial basically. Okay, yeah. Okay. Can you see the screen? Like the question? Should I zoom in?
No, ma'am. It's readable. Yes, ma'am. Legible.
Okay,
Yeah.
great. Okay, feel free to ask any question. Okay, one more minute. Okay, I guess that's okay. Okay, so as you can see the question, consider a finite group G. Okay, group is given to be a finite group, and there's a condition on this group that any two arbitrary subgroups H and K, either H is contained in K or K is contained in H. So basically it is saying that it has partial order in the subgroups um, with the order to be containment. Okay, so let's see what is the question. So G is given to be a finite group, and if you take any H and K, then either H is contained in K or K is contained in H. Can anyone give me an example of such a group, just for understanding the question? Take any small group, then you can have this condition.
Z and 2.
Sorry, come again.
Z2.
Z2. Very good. So yeah, can you explain to everyone? So Z2 is 0, 1, right? And then what are the subgroups?
0,
Yeah, 0.
1.
1 is a subgroup. So Z2 is with addition. So can you consider a subgroup like this? Yes or no? Think about it. If you take this as a subgroup, yeah. Yes, Chinari?
No.
No. Why? Reason?
Because closure property doesn't.
Yeah. Right. So if you take 1
Yes.
plus 1, yeah.
There's only one element in this set, so it
So
can't be a group. Yeah.
what is the problem? Like here also, this is just one element.
But for zero, we are able to find inverses. For one, we would not be able to find inverse.
So like yeah,
Yeah.
as yeah,
Yeah.
you can take from any side. Like so, as Chinari said, closure property will not be satisfied. So one, if you take 1 plus 1, then that is 0, because we are in Z2. So we are going mod 2. So this is not a subgroup. So what exactly we can take as a subgroup? We can, so if we have 1, then we have to have 0, because 1 plus 1 is 0. So basically if you have 0, you just have two subgroups, 1 and 2, like this one and this, which is the whole group. So what we were checking, so since there is just two subgroups, so actually these are trivial. So it's like we have, if you take this and this, then what condition you have? That 0 is contained in 0, 1. So this property is satisfied, like which it was saying, like if you take any two subgroups, then there must be some relation, either H is contained in K or K is contained in H. Okay, very good. So we have an example for it. So I hope you understood the question. If not, just let me know. Okay. Yeah, so let's come back to the question. So it has been asked what G will be, like either G will be a cyclic group or abelian, or it will have two proper subgroups, or both A and C. So we have to check what G exactly is. Okay, let's see. Okay, so for to check this or to prove this or whatever we need to find out what G is, let X maybe yeah, X be an element in G of highest order. I hope you know what is order, which we discussed last time also. So what is an order? Order of X, what does that mean?
X power m is equal to e, then where m is the
Yeah,
smallest integer.
yeah, smallest non-negative integer. Or actually we cannot take 0, so it's like positive integer. Okay, so this is the order. So let X be an element in G of highest order. Okay, now let's see what we have. So I'll just erase this, as you all know. Okay, what is this? Generated by X. So what this is a subgroup, right? If you don't know this notation, I can explain. So this is basically what? X square, x cube, whatever it will have, up to it will go wherever it will go. So since this is of, so okay, one more thing, why I can say this is highest order? Why highest word will exist here? Can you tell me?
Because the highest power of x should contain the group.
No, that is right. Like, so basically I am saying why order cannot be infinite. So for example, if you have integers, then if you take 1, then the order of 1 is infinite, because 1 plus 2, 1 plus 1 plus 1 plus 1, so you will have all the integers. So and you will never come up with 0. So this is actually infinite. If any power, like 1 raised to power any power, is not identity, that is 0, then the order is infinite. So why, so in that case, if any element could have infinite order, like if order is infinity, then I cannot introduce the word highest. Can you tell me? Still I can write here why this is possible. You understand my question? Yes or
Yes,
no? So tell me why I can do this. Just read the question carefully.
For all elements, we check the order. Uh,
Yeah, and
uh,
there could
the
be,
value of m we should be highest. That is the order.
right. So because in infinities we cannot compare things, so still I am saying highest thing. Okay, so just read the question. What does this say? Consider a finite group G. There might be possible in infinity terms we could say highest or not, but in finite thing we can always say it. Why? Because if the group is finite, then there cannot be an element such that the order is infinite. If order is infinite, that means you have infinitely many elements in group G. Do you get my point? So for example, yeah. So for example, in Z, you have 1, 1 plus 1. So these are all different elements. 1, 1 plus 1, 1 plus 1 plus 1, up to and so on. Like you have like 1, 2, 3. So all these are different elements, right? So if order is infinite, that means you have infinitely many elements in G. So I am introducing highest word and still I am thinking of a finite value. So the order is some finite value. Okay, it is not going to infinity or something. So there could be a problem there, but at least in my case with the finite group, everything is okay. Do you get it?
Yes.
Okay, great. Okay, very good. So let's see what we have. Yeah. So here I am saying why I was saying, so here you have x square, x cube, and you will come up to identity definitely. Like there will be some power, like some order, the ordered value. Like this will be the order of x. So this will be identity. So this is some finite set. Okay. Okay. So let's see. Okay, I should add a page. Yeah. So now let y be an arbitrary element so now I have taken y to be any element of G. Okay, it's not it need not be of highest degree or highest order or something, but you have just any element y. Now again you have this is a subgroup of G. So you have two subgroups right now, y and x, right? Two subgroups you have. Now according to the question it says either h will be contained in k or k will be contained in h. So according to question there must be some relation. Maybe so either this or x is contained in y. There could be anything like either this or this. So let's check. I am claiming that maybe okay, I can write it in the form of claim. Claim is y is contained in x. This is not okay, I should not say this is not true because equality is there. This is possible that these are equal, but at least because if y is equal to x, then it is definitely equal, right? So I'm saying that this is true. Like it is not true that x is properly contained in y. Okay, this is not true. I'm going to prove that. So let's let okay ignore this. Now here finiteness coming into picture. Okay, so let's see what is this. Let's check what are the number of elements in this group. Okay, I'm not saying what is the relation between these. So this is the set of number of elements, cardinality of this set. So y is what? Y square, it will go up to y order of y identity. Sorry, not identity, because you will this term itself is identity. So you have this set and other side you have this set, like as we wrote earlier, and this is equal to x raised to power order of x. Okay, so you have two sets. Now can you tell me why this one is bigger or equal? It is possible, but it can never be smaller. This set
Because
is
it is a subset.
we
Y
don't
is
know that,
subset
no?
of x.
We don't know that. We have not proved this claim. Like, let's say these are two things right now. either this or this. We don't know what is going to happen, but we are claiming that this is less than or equal to this value. If this is true, then definitely this will be true and this will be false. False in the sense that this is not properly contained. Okay, so equality is always, equality could be there. Think about how x has been chosen. What is x?
Highest order.
Yeah, this is of highest order. What does that mean? What does that mean here? Think of, like, if this set is the number of elements in this set is bigger than this set, that means the order of y is bigger. Order of y,
Yes, ma'am.
right? So order of y is either smaller or equal to order of x, because x has been chosen to be of highest order. Is it clear? So this will happen. So this has to be true. So here we don't know the relation. So after this, you know that this is true. Are you with me? Is that clear?
Yes.
Okay. If you have doubt, just unmute and speak. Okay. So this is true. This implies, now we know that this is either, now you know either this is true or this is true. So you know that this cannot be true, like properly containment cannot be true, because number of elements in y is less than or equal to number of elements in x. So for sure this should be true, because one of them has to be true. It cannot be possible that there is no relation between these two subgroups. So this is true. Since y is chosen to be any arbitrary element, like it could be any element of or maybe one thing, better to write it in the form. What does this imply? That this set is contained in this subgroup. That means y belongs to this set, because we are saying this set is contained in this set x square up to and so on. That means y, which is here, must be from this, like must be here. That means y belongs to subgroup generated by x. Since y is chosen to be arbitrary, this implies, now you know, now y is anything, like y is any element of G. Now you know that y has to be in this set. That means full G is a subset of x, right? And since x is an element of G, this implies, you know that this is a subset of G. This is not implies, this is from the beginning, because x is an element of G. So this this subgroup has to be in G. This implies G is exactly equal to this subgroup group generated by x. Is it clear? Just let me know if you have any doubt. Yes, Janari? Clear?
Clear. Clear.
Okay, great. If you have doubt, just unmute and speak. Anyone? Okay, so tell me what is true now in these four options. What can you
G
conclude?
is cyclic.
G is cyclic, exactly, because G is turning out to be this set, like generated by x, and cyclic means it is generated by x, or actually you can write it n into like G is isomorphic to Zn. This is also a way to write it. finite group, or it's just generated by one element, so it is cyclic. Okay. Second one, G has only two proper subgroups. Okay, let's come to this part a bit later. G is abelian? Abelian or not? Yes. Yes, Anugrah. Yeah. So G is abelian. Very good. Because all the cyclic groups are abelian. And so both A and C are true. Now let's come to the second part. G has only two proper subgroups. Okay. So I guess example is here only. So as you told, example, you can consider this example. Does this set has two proper subgroups? So okay, proper could be have two definitions. Either you can consider identity one to be a proper subgroup or not. That is your choice. So okay, let's say for now identity. Okay, so I am saying proper subgroup means no non-trivial subgroup. So we are not considering identity 1 and the group G. We are not considering this. Okay, should I change my color? Yeah. So that means identity and G is we are not considering as proper. Okay. So here if you see, here you have just two subgroup. This is identity and this is the full group. So actually you have no subgroup here even. So definitely this is wrong because G has only two proper subgroups. Here you have no proper subgroup, right? So you have this example. So this example will work for B, and this says B is not true. Is that okay? Okay, great. Okay, so both A and B is A and C is correct. Okay, let's come to this question now. Okay, so an automorphism is an isomorphism from G to G. So okay, you know what is an isomorphism? Okay, so I'll just ask you, what is an homomorphism? So you have let's say G1 to G2 phi. Then what is an homomorphism? So these are two groups. We are saying
phi of A dot B is equal to phi of A into phi of B.
very good, yeah. So phi of A into B. So operation could be different. Let's say G1 is with this and G2 is with the operation. Let's say this one, kind of off. Okay. So phi of, if you take two elements here, the operation will be this. And here you will get phi of G1, and now the operation is this, phi of G2. So this means homomorphism. Like if this is true for all elements, for all G1 and G2 belongs to G1 and G2 belongs to G1. Oh, I should have taken A1, B1. It will not confuse you. Yeah, you can take AB. Yeah. Okay, so this means homomorphism. Now we are seeing isomorphism. What should we add with homomorphism?
1 and none by length.
Yeah, exactly. So homomorphism plus 1 plus onto implies isomorphism. Now with isomorphism, if you add the property that G1 is equal to G2 with the same operation, okay, same groups, and like star is same as off, So G1 and G2 are same. So if you, let's say this is, or maybe I'll just write this, G1 star is same as G2 of, not even saying this isomorphism or something, it's just the same groups. Okay, let's say this is, or maybe if you say the domain and codomain is the same group, then this is a automorphism. Okay, so here the question comes. So an automorphism is an isomorphism from G to G, okay, where G is a group. So if you take both G1 and G2 to be same, then you are in automorphism. If this is an isomorphism also. Okay, which of the following are automorphism? Okay, so let's see. So to prove an automorphism, we have to prove all these property, like it should be homomorphic, this should be an homomorphism, it should be 1 2, it should be on 2, and the groups are given to be same, like it is already they have already said that this is going from G to G. So you have, so let's take first one. T is given to be a map from G to G which says x goes to x inverse. Okay, now first you will prove homomorphism, right? Let's check if this is an homomorphism. So what you will do, just take two elements, let if you want to take A and B, that will be good, no doubt. A and B belongs to G. Then what will happen? Should I take XY? This is like convenient here. XY belongs to G. Now, okay, so for homomorphism, you have to check that this property is satisfied. So let's take T, X, the operation, let's say this is this, or you may just skip it. You can also write XY this. So it is understood, so there is no issue. Okay, so what is this? T is saying it is mapping it to inverse of this, x star y inverse. Okay, map says whatever element you will take, it will take it to the inverse. And if you know, so what is inverse of x into y inverse? Sorry, what is
x inverse.
Yeah, y inverse x inverse. You can skip this operation. Yeah, and what is y inverse? Y inverse is t of y, right? Because x inverse is like y inverse is what? If you map y to in this notation, you will get t of y is y inverse, and same as x. Also, you know that since it is not given that what is group, so we will assume that this is a commutative group, unless it is not stated, like unless stated it is a commutative group. Okay, right, so you can actually write t of x star t of y. So this is true, t of x star y is equal to t of x t of y. So first property is checked. Second, 1 okay, for 1 what you will check? T of x, if t of x is equal to t of y, then x has to be equal to y, right? So here you have given that this is x inverse, this is y inverse. Now what you can do, you can multiply with x, right, multiplication, and here you will have identity. I don't need to write it, this is identity of G, or because there is just one group, so we have no problem. Is the identity of G. Okay, so this is E, this is y inverse star x. Now multiply with y. So you will get, actually you could have taken inverse here directly, but that's okay. So this is y star y inverse is identity, and this is x. So you get y is equal to x. So 1 is checked. So tx is equal to ty, then y has to be equal to x. Okay, third property. Okay, can anyone tell me onto need not be checked if g is given to be like, okay, I'll just state it. This is a fact, you could say. Onto we need not to check if g is given to be an finite group. Like if g is finite, then it is enough to check just one property. Either you check 1 or you check onto. That's okay. Can you tell me why? If g is finite. If g is infinite, we cannot say that. Either you check 1 or onto, other one is implied. Like if 1 is true, then definitely onto will be true. Or other way around, if you take onto, then 1 will be true. Only if g is finite. Can you want to try? Like, okay, just think of what will happen. If g is finite, that means it has finite number of elements. Let's say n elements. Right? Okay, I'll just change the color. If this looks messy, just let me know. Like, I'll try to keep it fine. Okay, so g has, let's say this is n, the set has n elements. It is not about just group, it is about anything. Like if you have to check onto 1 onto, then you if the set is finite, then you don't need to check the other one. Like if one is true, then other has to be true. So why this will happen? So you have n elements and you have n. Only if the sets are same, like also the set has to be same. So for example, you have n elements, let's say x1, okay, x1, x2 up to and so on, xn, and here you have x1, x2 up to and so on, xn. So what will happen if you check 1 that means every element has been mapped to only one element. Let's say here whatever it is. So every element has exactly one image. Sorry, every element for one thing, what does that mean? Like every element here in the range has single pre-image. Like only one element has been mapped to that element. So what does that mean? Like you have exactly n elements here, and this has been mapped to different elements. Like here different elements, that means that has been mapped to n elements, right? And now for ontoness, what does that mean? Like if you take any element this side, it should have a pre-image, but you already know that n elements has been mapped to n elements. So all has been covered here. So 1 means n elements n elements mapped to n elements. So there is no element in the domain which is left now. So that means onto is there already. Is it clear?
Yes.
Yeah, very good. So other way around also, if you take onto property, that means onto means all the elements here has pre-image. Okay, and now you have already said like all the elements here have pre-image. That means yeah, how shall I say, here you have n elements and pre-image is exactly n elements. So you have 1 and 1 also, because it is not possible that is it clear or
Then it can be many one function.
yeah. So Yeah, you have an element, so they have pre-image. So they have pre-image and you have an elements here, so it has to be 1 1. Okay, so for here
It can be many one.
it cannot be, no, because elements are n only. So what is given, that you have x1 x2 and xn, right? And you have x1 x2 and xn. You have all the elements have a pre-image. Okay, so there is one, or there is one, or maybe like this. Now you know that these are finite elements and this is a function, so every element has a image. So n elements, it is not possible that two same element has two image. If this is true, for example, if this is true, then one element has to be like is left, like, because you know that function one element cannot map to two elements. Just count in this process. For example, if x2 has two pre-images, x2 and x3, that means two elements has been used. Okay, and other elements has the pre-image, so there must be n minus elements, uh, at least n minus elements other than these two. But you know, then the set has n plus 1 elements, and then there will be a problem. Is it clear?
Yes, ma'am.
Okay, so basically, but in our case, so it is just for information, because sometimes if it is given just finite, you can check just one property and get rid of it. Okay, so let's see what do we have. So this is commutative, no doubt. Okay, so here this is not given to be a finite group, so we have to check the other thing. So okay, so for ontoness, what you will take, let y belongs to G. Now you have this G to G where x goes to x inverse. So y belongs to G. Can you tell me a pre-image for this element? Can you tell me what element I will take which will map to y?
Y inverse.
Y inverse. Very good. So because y inverse, when you map, this t of y inverse is equal to y inverse of y inverse, which is exactly y. So you have pre-image also, right? So this is onto, this is 1 1, and this is a homomorphism. So this is true. So first is true. Second, x goes to x identity. Is it true?
Yes. Yes.
Yeah, you can easily check this is a homomorphism, because nothing has been changed. Here you will get just a star b, and here again a star b. No change, right? And 1 1 onto true. Okay. Okay, let's come to this part. Is it true? If this is not true, we have to give an example. So definitely this is not true. Not definitely, but at least here it is not true. Can you give an example? Just again think of some small sets or small groups.
Phi of A.
Sorry?
Phi of A B is equal to A B. Phi of A square into phi of B square.
Yeah, that is a problem. Phi of A star B, if you take, that is A star B square, and phi of A. Oh, no. So what you are saying, this is not a homomorphism.
Yes.
Okay, let's check it. So phi of A star B is A star B square, and that is like A star B, and these are actually commutative. If you write it repeatedly, it is, you can actually write A square B square. So star, if you want, you can keep it. So this is just A square B square. Here you will get A square star B square. So this is same. This is a homomorphism. Is it okay? Others? 1 and root 1. Okay, so sorry, I didn't get it. What is root 1? Oh, you mean root minus 1? I think you mean root minus 1, otherwise root 1 is just 1. Is it okay? Anugrah? Taking the root of 1. Okay, root of 1 means what?
Plus or minus.
Oh, okay. Okay, so root 1 is never plus 1 minus 1. This is plus minus root 1. So if you want to say, you can say the roots of this equation. If you say root 1, then it is already plus. So this is not actually what you want. So you can or maybe you can say positive root and negative root, but if you say root already, then it is assumed to be plus. But okay. So you can actually say roots of x square is equal to 1. Roots of x square is equal to 1 in uh, in real numbers or something. Anyway, it's fine. Okay, so yeah. Okay, as you said, this you have taken 1 and minus 1. Okay, so 1 and minus 1, yeah, you have taken g to be this, and what is the operation? Operation is
X square. F of x.
no, operation means what is the, like, how you are multiplying, adding or something. So this is multiplication definitely. Yeah, 1 is identity and minus 1 is the other element. So if you take 1 and minus 1, and if you map it, here you have 1 and minus 1. So 1 goes to 1 because 1 square is 1, no doubt. Operation is multiplication. And minus 1 square is equal to 1. Right? Very good. Yeah, exactly. This is a correct example. So if you take this, then you can see this is not onto. See, this is you have taken finite groups, okay, and onto is not here, so 1 is also not true. So you can see, which I was saying earlier. Okay, so this is an example which says that t x to x square is not an isomorphism. This is still an homomorphism. Okay. Okay, let's move to the next question. So which option is correct here? This one, option A and B. Is it okay? If you have doubt, just unmute and speak. Okay. Suppose G is a cyclic group and H be any subgroup of G, which of the following statement is true? So G is given to be a cyclic group. Okay, let's have what we have. You have G is given to be cyclic. So can I write it is generated by some element X for some X belong to G, because this is a cyclic group, so it is generated by just one element. And H is given to be a subgroup of G. Now they are asking what is H. Can you tell us about what is either H is abelian, cyclic, or finitely generated, or like all of the above, or none of these? It could be anything. Let's see what we have here. Okay, so okay, what is your guess? Or you may tell me the proof also. Just you can have a wild guess. Think about it. Okay, let's see what it is. G is given to be generated by X. Now H is a subgroup, so let's see what are the elements of H. Can we say anything about elements of H? Let okay, the elements of H or any element of G, how it will look like? It will look like X raised to power something, right? Because G is generated by X, this means x square, x cube, it will go up to x raised to power order of x, because this is just identity, this is equal to identity, right? So order of x is just a number, and we know that that number is something which says x raised to power m is equal to identity, if it is m, for example. So all the elements will look like x raised to power something. So again, since H is a subgroup of G, all the elements will look like some power of x. Let x raised to power I be the smallest power of x in G. I can say the, no doubt, because this must be some unique element, right? Smallest power of G, this is a smallest power of G, and I'm talking about positive ones, okay? X square, smallest positive power of x in G. So this is the smallest one. Now claim is H is equal to generated by x raised to power I. So I'm claiming that H is actually generated by this x raised to power I. So don't be confused with this I. This is just any element of so all the elements will look like x raised to power, let's say k or something, and I'm saying I is such that x raised to power this is the smallest power in G. Okay, so let's prove that. I'm saying that H is actually generated by this element. Okay, let's say if not, or maybe you can write assume the contrary. What does that mean? H is not equal to x raised to power I. H is not equal to subgroup generated by x raised to power I. What does that mean? There exists some element x raised to power j. That means this implies there exists, or I can write it, there exists x raised to power j belongs to H such that, can you tell me what does that mean? X raised to power j is such that, okay, one more thing, x raised to power I belongs to H, that means all the powers of x raised to power I belongs to H. That means this set is contained in H, like full generated set is in H, because x raised to power I will be there, x raised to power I square will be there, x raised to power I cube will be there. So all the elements will be in H. Okay, so this is contained in H. I am saying this is our claim, and we have assumed the contrary. That means we are assuming the negation. We are proving by contradiction. So that means this is properly contained. This is not equal, because already we know x raised to power I generated this set is contained in H. That means if we are saying these are not equal, that means there exists some element in H which is not in this, right? So there exists some element of H, that means it will again be some power of X, because G, the bigger group is some all the elements of G are the powers of X. So there exists x raised to power j in H such that x raised to power j does not belong to this set. So what we are saying, we know that this is contained for sure, right? This is contained, but we are saying this is not equal. That means this is not equal. Okay, we are assuming that this is not true. So this is not equal means there exists some element, in H such that some element, let's say G, some element G in H such that G does not belong to x raised to power I, like set generated by x raised to power I. And now you know what is G. If if there is an element of H, that means that is an element of G. That means this must be some power of X. So we are saying this x raised to power J does not belong to x raised to power I, set generated by x raised to power I. This means exactly this. Is it clear what the negation here means? Maybe yes or no? Okay. If you're not following, just let me know. Okay. So this is the case. Now you are saying x raised to power J, x raised to power J belongs to H, and x raised to power J does not belongs to x raised to power I. Now what does that mean? This means x raised to power J is not equal to any element of x raised to power I, this generation, that the set is itself is x raised to power I, x raised to power 2I, x raised to power 3I, like this. So x raised to power J is not equal to x raised to power Ki for any k, right? This must be true, for any k in maybe natural number or whatever you want to say. Is that okay? So we know that this is not in this set. That means x raised to power cannot be written as of this form, right? So this implies what do we want to say here? J is not equal to Ki for any k belongs to n. And this implies, now what you can use, you can actually write J is equal to, okay, I should not introduce k here, but that's okay. Let's take new variables here, maybe R or S. Now I have used division algorithm. You are dividing by I. You have quotient and remainder. Oh, I can write quotient and remainder form. So I mean quotient and remainder. So you have quotient and remainder when you are dividing by I. J is equal to okay, yeah. Now this implies what is and here in division algorithm, so what we have taken, we are saying J is not a multiple of I. That means J is something multiple of I plus R, where R is strictly less than I. Is that okay? This is your divisor, and you know this remainder has to be smaller than this divisor. Is that okay?
Yes.
Okay. So from this, what you know, x raised to power J is equal to x raised to power Qi plus R, and this is equal to x raised to power I raised to power Q into x raised to power R. And now you know x raised to power J, and you have x raised to power I raised to power Q raised to power minus 1 is equal to x raised to power R. And now you know x raised to power J belongs to H, x raised to power I belongs to H, so its any power will be here, its inverse will be here. So this element, so these two elements will be in H, and these two elements are in H. This implies this belongs to H because of closure property. H is a subgroup. So this implies and this value is exactly equal to x raised to power. This implies x raised to power r in h, where r is strictly less than I because of this property. And this is saying r is strictly less than I. That means this is a contradiction to what I has been chosen. I is saying this is the smallest positive power, sorry, x in h, sorry, smallest positive power of x in h, because we are talking about h. And so what we have taken g, and then there is a subgroup h, and now you have taken any element of h which has smallest power of x, because all the elements are look like power of x. You have picked up the smallest power of x from h, and then you are saying that element generate the set h, generate the group h. And now it is saying that you have come to a point that x raised to power r this belongs to h, and r is strictly less than I, but you have taken I to be the smallest in this case. But x raised to power I is such that, or maybe you can write it in a better form, but I is such that, or I is the smallest integer such that x raised to power I belongs to h. Now you are saying x raised to power r belongs to h, where r is strictly less than I. So this is a contradiction, and you have a contradiction to the thing that we have assumed that this is not true, and we arrive at a contradiction, and this implies h is exactly equal to x raised to power I, like generated by x raised to power I. Is this clear?
Yes.
Okay. Okay, and because of this, which option is correct? You can write it in the chat box. Others, please feel free to speak.
H
Yes,
is
sir.
cyclic.
Sorry. Yeah.
H is cyclic.
H is cyclic.
And
H is
and
abelian. Very good. And is H finitely generated? Okay. That's okay. Yeah, H is finitely generated. Finitely generated means finite number of elements generate the set. Here if you see, there is just one element which is generating the set. So H is actually generated by just one element. Generated by, this means finitely many. Here H is generated by just one element. So this is true, and because of this, all of the above. Okay. Okay.
yep. Once you explain the meaning of finitely generated.
Oh, yeah. So finitely generated means if you say G is finitely generated, this implies G is generated by some G1, G2, or okay, better to write. This implies there exists G1, G2 up to and so on, Gn. There is some fixed n belongs to G such that if x belong to G, this implies x can be written as some power of, let's say, n1, g2 raised to power n2 up to and so on, gn raised to power, okay, there is some n, too many n's, yeah. So you can take actually, let's say, p1, p2, these are just numbers, okay. So any element can be written as the product of powers of these GIs, like these should be finite, so n is some finite number. So we can actually write G to be G1, G2, generated by. So this is the symbol for generated by. So you can actually write it in this form. So this is finitely generated. Is that clear?
Okay.
Okay, let's move to the next question. Suppose A is given to be Z8, B is given to be Z2 cube, which is actually Z8. So 2 cube is just 8. So it is not saying something different. Okay. So this is Z8 if you remember. So these are with addition. So it's like 0, 1, 2 up to and so on 7. Right. And here this is the same thing. If you write just in, so this is just a number. You have written it in the different form and that is same. So now for third one is this. So what is this? Z4 is 0, 1, 2, 3 and Z2 is 0 and 1. Right? This is this set. Okay? And D is given to be Z2 cross Z4. So this is 0, 1 and this is 0, 1, 2, 3. Okay? So this is the set. Now it has been asked that which of them are isomorphic to each other. Okay, A and B are same. So it's just A is isomorphic to B. Okay? So this is not something which is different. So A is isomorphic to B, no doubt. Now, can you tell me if C is isomorphic to D? So isomorphic means you should be able to define an isomorphism between these groups. So that means there should be some phi from C to D such that you can map every element of this to D. So this is the point. Okay. So can you tell me an isomorphism between C and D? So this is just Z4 cross Z2 and this is Z2 cross Z4. So you have any element A, B, let's say here. Where will you map? What is the natural idea? Like, what can you say? Where will you map? So just if you see these C and D, what is that? Z4 cross Z2 is now Z2 cross Z4. So what will you do with AB? Yeah. Yes, Kamal?
BA.
Yeah, exactly. Very
Yeah.
good. So you will just switch as per the even itself the group saying that. You will just do this and now what you have, so you need to check that this is an isomorphism. You can see that this is 1 1 on 2 because these are just Z4 cross Z2 is not Z2 cross Z4. Now you can check this is an homomorphism also. Just check it. So this is this map. Check if this is not if, or maybe I'll just write verify that this is an isomorphism. Okay, now the question comes. Now you know two things. No, A is isomorphic to B and C is isomorphic to D. Now you need to check if there is any relation between these two, like either B is isomorphic to C, or it's just enough, like you can take anyone here, and you need to check if these are isomorphic or not. So really the question is Z8 and Z4 cross Z2 are isomorphic. Sorry, this is with R Z8 and Z4 cross Z2 isomorphic. That is your question. Okay. Okay. So let's say if there is an isomorphism, let phi is from Z8 to Z4 cross Z2. Let's say this is an isomorphism. or maybe just take any phi. Okay, now or maybe let's say be an isomorphism. So the question is, does this really exist? If it is not, then there must be some contradiction here. So here 1 definitely. So Z8 is what? Z8 is 0, 1 up to and so on 7. So these are the elements. 1 must be mapping to something. Let's say A comma B. And actually that's enough because Z8 is generated by 1. Okay, so you have, so definitely there is a map, so you must be having 1 is there and 1 has been mapped to this side, which is like, let's say A comma B. Okay, can you tell me where 0 will go? 0 is identity here. Where will it go? So this
0 cross 0.
yeah.
0, 0.
Yeah, 0 comma 0. Yeah, cross is there. Exactly. So in an homomorphism, this is always true. Identity will map to identity. You can actually prove it if you need. You can actually use this if you want. So phi 0, you know that this is true. And here you will get phi 0 and here you will get phi 0 plus phi 0. And actually here you write identity plus that element and then you just take the inverse of this. So you will just get this. So this is a way to prove it. So identity will always map to identity. Okay. So 0 means like here identity is there. So I'm not. So for proving you can just take identity of G and G1 and identity of G2. So you can prove it. Okay. So phi 1 will go to A comma B and you know 0 will go to 0 comma 0. Now let's say where phi 1 plus 1 will go. So phi 1 plus 1 is what? Phi 1 plus phi 1 because this is an homomorphism. So phi is an homomorphism. So this has to be true. Now see, phi 1 plus 1, that is phi 2, is equal to phi 1 is what? A comma B. And here again A comma B. What you will get? Phi 2 is equal to 2A comma 2B. And just see, 2B belongs to Z2 and this belongs to Z4. What can you say here? So Z4 one we don't know, at least you can write 2A. What can you say about 2B? This is in Z2. That means this has to be 0. If it is a multiple of 2, it will go 0. It will be 0. Right? If you add B plus B, this is coming with 2. So this is 0. Now this is true. Now if you check this, what so we need to go to 4 also. Okay. So 2 plus 2, this is equal to since, so phi of 4 is equal to, phi of 2 is 2a comma 0 and this is 2a comma 0 and you will get 4a comma 0. This belongs to Z4. So this is again 0 comma 0. So what this is saying, phi 4, so this is saying phi 4 is equal to 0 comma 0, but 4 is not equal to 0 mod 8 because this is an element of 8. Okay, Z8. So 4 here is not 0. So you have a problem that phi of 0 goes to 0 comma 0 and phi of 4 goes to 0 comma 0. So onto is not true. So this is not onto. So problem occurs. Yes, Janari?
Ma'am, can you explain it? Why the Z2 value?
Sorry?
2B value? Why do-
Can you tell me which step?
Phi of 2 is equal to A comma 2B. Then next step.
Okay,
Phi of
phi
2 is
of,
equal to A comma 2.
this is true, this is okay?
That is not. How
Okay.
that step?
How that step? Okay, so why 2b is equal to 0 you mean?
Yes.
Okay, so we are in Z2. What is Z2? Z2 says you are going mod 2. What does that mean? Z2 is all the integers integers mod 2. Z2 means this. Now 2b is what? If you take mod of that, what will you get? So mod, okay, 2b is what? 2b mod 2 is what? Tell me. This is 0?
0.
So this is exactly 0 mod 2. So Z2 means you are going modulo 2, and because of this is 0. And now here this will be 0 because this is 4a. Now you are going mod 4. Here I cannot say about 2a here because this is just saying mod 4 not 2, so I cannot do here anything, but here I am surely I can surely do something that 4 is 4 into something, and if you go mod 4 you will get 0.
Okay.
Okay, great. So on 2 is a problem, and you have taken any general isomorphism, so there cannot be an isomorphism here. So here this option is correct. So this is saying A is isomorphic to B, C is isomorphic to D, but not B or D or B or C, whatever you want to say. Okay, so let's come to this part. If a group G does not have a non-trivial subgroup, then G is what? So let's see. So G does not have a non-trivial subgroup. That means you don't have anything like other than, so non-trivial subgroup. So what are trivial subgroups? Trivial subgroup means identity, exactly, and the other one is G itself.
Okay.
Right? There are just two groups. Two subgroups. Now it is saying there is no non-trivial subgroup. That means there are just two subgroups here. So G has two subgroups, E and H, only two subgroups, E and G. Okay. Now let's see what does this say. Okay. So first step you can say let G is equal to identity. If G is identity, so okay, my claim is, so what I am going to prove, that G is finite, that C option is correct. Okay, so to prove this I will take some cases. So first case 1, that G is equal to identity. So if G is identity, just identity, then definitely G is finite, right? There is no issue with that. Finite means just finite number of elements. Finite number of elements. G has finite number of elements. Nothing else. So there is just one element here, that means this is finite. Okay, now come to case 2. G is not equal to identity. Now assume G is not identity. What does this imply? There exists X in G such that X is not identity. That means, like there exists some non-identity element. Okay? Non-identity element means X is not identity. So there exists some X. Now you know that there are just two subgroups. Now if you take this subgroup, you know that there is a subgroup which is generated by X. Now you know that this is not identity because X is not identity, so this cannot be equal to identity. This means this has to equal to G because this is a subgroup, and subgroup has just two options, like either identity one or G. So this has to be G, the full group. Is it okay?
Yes.
Okay. So you have this condition. Now, okay, so X is equal to G. Okay, what can I say here? Okay, yeah. Now I am taking subcase 2a. Okay, subcase 2a. Now what does this say? I am saying x square is identity. If x square is identity, that means this set is what? This set is equal to just x comma x square, sorry, because you are saying x square is identity, that means you have just x and x square, and this element is identity, so you have just this set x comma identity, and you know that this is G because you know this is G. Okay, so you have just two elements, G has two elements. So again this is finite, G is finite. Now take another subcase. Now obviously subcase you have to take other condition. What condition could be possible now? X square is not equal to identity. Exactly. So here what will happen if x square is not identity? Again, because of the same reason, this has to be G, because x square is not identity. So this is a subgroup. Then it has to be the full group because there are just two options, either identity or G. So this is identity. This implies x belongs to x square. Why I am saying that? Because G is already x, right? Since G is already x from this step. Okay, so okay, I can write it better. So you know that x is equal to x square. This implies x belongs to this set, like x will be here. What does that mean? X is equal to some power of x square. That means let's say x square raised to power k, because all the elements of this generating set, like the set generated by x square, will look like x square raised to power something. So x has to be of this form. This implies x is equal to x raised to power 2k, and this will say, and this is a finite number where k is a positive number or whatever you say. Here you will get now you multiply by x inverse. Yeah, so you will get this, you will get identity, this you will get x raised to power 2k minus 1. So this implies this set, which is actually G, where we begin. So this is G. This is equal to x square up to and so on. It will just go till 2k minus 1. So, and this is a finite number, right? Because it will go, so this set is what? X square, x raised to power something, until you will reach identity. So this is a finite set. So again this will imply G is finite. Is that okay? So we have covered all the cases. Okay, nothing is left. We have taken this and then this, and into this one we have taken sub cases. Okay, I will just end up with this last question. Okay, what is the necessary and sufficient condition? If you have doubt, just let me know. Okay, what is the necessary and sufficient condition for an integer k to be a generator of Zn? Okay, so the question has been asked to be, okay, you have taken, there is some k and it belongs to Zn. Okay, now you are asking, the question is asking, if you generate by k, this is equal to Zn. When will it happen? When will? So this is your question. What k you choose such that if you generate by k, then you will get full Zn. So that is your question. Okay. Yeah, tell me. Yes, Kamal?
Oh, GCD1?
Yeah, exactly, GCD1. So we'll prove it. So
Yeah,
can you tell me where can we begin?
Yeah, I was just thinking, so if assume that k divides n or n divides k,
Okay.
so that means for generator, so
Yeah.
it will be some multiple of n is some multiple of k. So I would
Right.
only be
Let's
able
say.
to.
Yeah. You will only be able to have the powers. Yeah.
Yeah.
Exactly. So yeah, you are going right. No doubt you can actually find examples, like you can find some counter examples with these cases.
Yes, ma'am.
But again, we have to prove it, because there could be a fifth option which says none of the above. So right, so we cannot always choose like this, but so we should have a proof. Okay, so, and it says necessary and sufficient condition. That is important. It is not saying just one side, it is saying both sides. Necessary and sufficient condition for this to happen. So let's say if it is given that k is equal to, or maybe I'll take the other direction first. I don't know which side I should write, but whatever it is, let's say one direction, let GCD of nk is equal to 1. Then you know that you can find some okay, then what can you say about this?
Linear combination, we can find
Yeah.
some x, y such that nx plus ky is equal to 1.
Exactly, very good. So you have some x, y in integers such that n xn plus yk is equal to 1. Exactly. So now what you want? You want k should generate zn. What is a possibility? Like zn is what? Zn is a set 0, 1 up to and so on n minus 1 with addition. So if you can find out that 1 is there, like if you generate by k, if 1 is there, then everything is there, because 1 plus 1 is 2, 1 plus 1 plus 1 is 3, and you can have till n minus 1. So if 1 is there, then you have everything. So it is enough to check, it is enough to verify, not verify, enough to show that 1 belongs to k. If 1 is there, then you have full set, right? Full Zn you will be having, because if 1 is there, then 1 plus 1 is there, and you can go up to n minus 1. These are n minus 1 elements, and you will get n minus 1. And if you add again 1, like n elements, then you will get 0, because this is mod n, so you will get 0. So it is enough to have 1 here. Okay, so let's see if we can do that. You have xn plus yk is equal to 1. Now if you want to say that 1 is there, then you have to write 1 as a multiple of k with mod n. You have mod n always. So what you can see here, you have yk is equal to 1 minus xn, and if you see, you can write yk is equal to 1 mod n, because if you go mod n, this is just a multiple of n. So if you go mod n, this will become 0. So you have just 1. So yk is equal to 1 mod n. So this implies, and yk, and you know where yk is. So yk is what? Yk is something like k plus k or something, or maybe it could be negative, so it could be minus k, because k is there, so minus k will be there, right? Because k is it is generated by k, so you will be having minus k, and you are in finite set, like Zn is finite, and inverse of k is minus k, so that is there. Whatever it is, you will be having that. So yk definitely belongs to this set, right? Because this is just k raised to power y, if you think of in the form like, okay, the operation is addition, so k plus up to and so on y times, so this could be minus or whatever. Okay, so this is there, and this implies, and yk is turning out to be 1 mod n, so 1 mod n, or you can write 1 directly now. So this belongs to k. So this implies if 1 is there, then as you have proved that the full set will be there. So k is equal to Zn. Is that okay?
Yes, ma'am.
Okay. So let's prove the other side. I don't know which side. Okay, this arrow I am confused a bit, but that's okay. So other side. Now you have taken let k is equal to Zn, like this generates Zn. So again, as you know, this is in this, so that means 1 belongs to k, right? Because Zn
Yes.
is in K. Yeah. So 1 belongs to there. So that means 1 is equal to some multiple of K. Again, mod n will be there. So let's say some Rk mod n, right? So 1
Yes.
must be some Rk mod n, and this will imply if you go, so mod n is there, that means there is some multiple of n. You can remove mod n and you can write this. And this actually implies GCD of, and the R and S are some non-negative, some integers. So, RSN. So you will get GCD of K and N is equal to 1. Okay? And you have proved it. So this is definitely if and only if condition, and it says this. Okay, this is the end of tutorial today. Is it okay? If you have doubt, just unmute and speak. Kamal, Samriddha, Chinari, Anugrah. Is it okay?
So far, okay. Yes, ma'am.
Okay, very good. So, yeah. So, if you have any question, just let me know. Otherwise, I can end the meeting.
Thanks, ma'am.
Yeah. Thank you. Sure.
Thank you.
Yeah.
Thank you.
Yeah. Thank you.